Good morning, ma'am. I'm Satvika from CSC department. I'm going to present a topic on Q networks, deep Q networks, and policy optimization as a part of our subject Artificial Intelligence and Expert Systems. These topics belong to the branch of reinforcement learning, which is one of the most exciting and practical areas of AI today. Now let's start with Introduction to Reinforcement Learning. Reinforcement learning or RL is a type of machine learning where an agent learns by interacting with its environment. Unlike supervised learning where we already have corrected answers, here the agent learns through trial and error. It performs an action, observes what happens and receives feedback in the form of rewards or penalties. The main goal of reinforcement learning is to find an optimal policy. That means a strategy or set of rules that helps the agent get the maximum long-term reward. A common real-world example is the self-driving car. It learns to stay in the lane, follow signals, and avoid obstacles by continuously improving its behavior based on rewards. Next, let's discuss about Q function fundamentals. The Q function is at the heart of reinforcement learning. It helps us estimate how good a particular action is when taken in a certain state. In simple words, it tells us if I do this action in this situation, how much total reward can I expect in the future. The optimal Q function represents the best possible expected reward achievable from each state and action pair. Coming to the introduction to Q networks. When the environment is simple, we can store Q values in a table. But in large or complex problems, this becomes impossible. That's where Q networks come in. Q networks use neutral networks to approximate the Q function. They take the current state as input and predict Q values for all possible actions. This follows reinforcement learning to be applied to tasks with large scale state spaces like playing video games, robot control, or traffic management. Coming to the Deep Q networks overview. Deep Q networks or DQNs are an advanced version of Q networks. They combine Q learning with deep neural networks, making it possible to handle complex and high dimensional inputs like images. The breakthrough of DQNs came from DeepMind's famous experiment where a DQN learned to play Atari games just by looking at the screen pixels and performed at or above human level. DQNs use a special technique called experience replay, which helps us stabilize the training process by reusing past experiences instead of learning only from recent ones. Now let us discuss about the DQN's architecture. The architecture of a DQN usually includes convolutional neural network layers to handle image inputs, followed by fully connected layers that output the Q values for all possible actions. The model is trained by minimizing the difference between the predicted Q values and the target Q values. The difference is calculated using a loss function and network's parameters are updated through backpropagation. In this way, the DQN gradually improves its predictions and learns to make better decisions. Coming to the experience replay and target networks. One of the biggest challenges in reinforcement learning is that the data we get from the environment is highly correlated. To handle this, DQNs use two key techniques, experience replay and target networks. In experience replay, the agent's experiences, which include the state, action, reward, and next state, are stored in a memory buffer. During training, the model randomly samples from this memory, which breaks the correlation between samples and makes learning more stable. The target network is another copy of the Q network that updates more slowly, ensuring that the learning target does not change too fast. These two methods together make DQNs much more reliable and efficient. Now, let us discuss about the policy optimization in reinforcement learning. So far, we talked about Q learning, which is a value based method. Now, let's look at policy optimization, which is a different approach. In policy optimization, instead of estimating Q values, we directly try to improve the policy itself. That means we directly adjust how the agent makes decisions to increase rewards. Algorithms like reinforced actor-critic and proximal policy optimization belong to this family. These methods are very effective in continuous control problems like robotic arms or drones. Now, let us discuss about policy gradient methods. Policy gradient methods are a key part of policy optimization. They calculate the gradient or direction in which the policy parameters should be changed to improve performance. This allows the agent to learn complex and flexible behaviors and also supports stochastic policies where actions are chosen based on probabilities. This is useful in uncertain or dynamic environments where deterministic actions might not work well. Actor-critic algorithms. The actor-critic method is a hybrid that combines the advantages of both value-based and policy-based approaches. Here, the actor is responsible for choosing actions based on the policy, while the critic evaluates how good those actions are using a value function. The critic gives feedback to the actor to improve the policy. Because of this cooperation, actor-critic methods are more stable and efficient than using policy gradients alone. Advantages of deep Q networks. Deep Q networks have several advantages. They can handle high dimensional inputs such as images or sensor data without needing manual feature extraction. They also generalize well across different environments and can achieve human level or even superhuman performance in certain tasks. This ability to learn directly from raw data makes DQNs extremely powerful for real-world AI applications. Now let us discuss about challenges in Q networks and DQNs. However, there are also some challenges because Q networks use function approximations. They can face stability and convergence problems during training. They sometimes overestimate Q values, which leads to poor decision making. To solve this, techniques like double DQN and dueling DQN have been introduced. These improvements help reduce overestimation bias and improve overall stability. Now let us discuss about some improvements in policy optimization. In policy optimization, researchers have developed advanced methods like trust region policy optimization and proximal policy optimization. These algorithms introduce mathematical constraints to make the policy updates smoother and prevent drastic changes. They also manage the balance between exploration, trying new actions, and exploitation using what's already learned. Because of their stability, these methods are widely used in robotics, autonomous vehicles, and control systems. Now let us compare Q networks and policy optimization. Q networks are value-based methods that learn the value of each action and then use that information to choose actions indirectly. On the other hand, policy optimization methods directly learn and update the policy, which means they directly learn how to act. Both have their pros and cons. That's why hybrid approaches like actor critic combine both strategies to get the best of both worlds, better learning stability and faster performance. Now let us discuss about some applications. These techniques have a wide range of applications. Q networks are used in video game AI, robotic control and recommendation systems. Policy optimization is commonly applied in robotics, natural language processing, finance and autonomous systems. When combined, these methods help build powerful agents capable of handling complex real-world problems. Coming to the future directions in reinforcement learning. Looking ahead, the main research focus is on improving sample efficiency, that means making agents learn faster with fewer experiences, and scalability, so they can handle larger environments. Researchers are also exploring model based reinforcement learning, which combines prediction models with learning based methods. Other exciting areas include hierarchical reinforcement learning, where agents learn complex behaviors by breaking them into smaller tasks, and meta learning, where agents learn how to learn. Finally, we have come to the summary and let us discuss some key takeaways. To summarize, reinforcement learning teaches agents through interaction and reward based feedback. Q networks and deep Q networks are powerful tools that use neural networks for value based learning. Policy optimization methods, on the other hand, directly improve the decision making policy. Both approaches are complementary and continue to push forward the process of artificial intelligence, especially in robotics and autonomous systems. Thank you, ma'am, for giving me this opportunity.